Welcome to the Deep Dive, where we cut through the noise to get you the most crucial takeaways from complex topics. Today, we're diving into, well, the sheer magic of models. Ever wondered how engineers design something huge like a Boeing 747 or maybe a high-speed bullet train without building dozens of expensive full-size prototypes first?
Yeah, I mean, it seems impossible, right?
Exactly. They use miniature versions, but it's way more than just shrinking things down. There's this really powerful scientific shortcut at play.
Hmm.
Our deep dive today is all about dimensional analysis and modeling. And look, this isn't just some abstract engineering thing.
Not at all.
It's a fundamental tool. It helps us understand how physical quantities relate, simplifies incredibly complex problems, and even lets us predict behavior across totally different scales.
It's really quite elegant when you get down to it.
So our mission for you in this deep dive is to break down the essentials, dimensions, units, right, the foundations, and reveal this key rule of dimensional homogeneity. Then we'll explore the power of dimensional analysis itself.
Yeah, how it's actually used.
How it's used to design efficient experiments, predict outcomes for massive prototypes from these tiny models, and honestly, save incredible amounts of time and money.
Which is always good.
Always good. And we get some surprising insights along the way, too.
Absolutely.
Okay, so let's break down the essentials first. What exactly do we mean by dimensions and units?
Okay, so think of a dimension as like a fundamental quality you can measure. Length, time, mass. It's the type of thing you're measuring. No numbers involved yet.
This is the concept, length.
Exactly. Then a unit is how we actually assign a number to that dimension. So for length, that could be meters or feet or miles, whatever.
Got it. Dimension is the what, unit is the how much.
Precisely. And what's really interesting is that there are only 7 primary dimensions that form the basis of, well, pretty much everything else.
7? That's surprisingly few.
It is. You've got mass, length, time, temperature, electric current, amount of light, and amount of matter. Everything else is just a combination of these.
So something like force.
Force isn't primary, no. It's derived. Its dimensions are mass times length divided by time squared, MLT2.
Yeah.
But the key is just knowing it's built from those basic blocks.
Right.
And the truly remarkable aspect here, the thing that underpins so much, is this fundamental law of dimensional homogeneity.
Okay, homogeneity. It sounds important.
It is. It's basically common sense, really.
Yeah.
It's formalized. You can't add apples and oranges.
Right.
Every single term that you're adding together in a physically correct equation must have the exact same dimensions.
Ah, okay, so if you're adding different kinds of energy.
Exactly. Like, say, the change in total energy of a system, that's the sum of changes in internal energy, kinetic energy, potential energy.
Right.
All 3 of those components and the total energy change itself, they all have to have the same the dimensions of energy, which are ML22. They have to match.
Okay, that makes sense.
Another classic example is Bernoulli's equation for fluid flow. You've got terms related to pressure, velocity, elevation.
Uh-huh.
But when you break them down to their primary dimensions, every single additive term in that equation has the dimensions of pressure, MT2L.
Just consistent.
Perfectly consistent. And this isn't just, a neat theoretical point. It's a crucial error-checking tool for engineers and scientists.
How so?
Well, if you're deriving an equation or setting up a calculation, and you find terms you're trying to add don't have the same dimensions, you know immediately you've messed up somewhere.
Ah, like a built-in spell check for physics equations.
Kind of, yeah.
Yeah.
It's a really powerful sanity check.
Okay, so we've established this rule, dimensional homogeneity. Every term matches. But can we, actively use that principle, go beyond just checking for mistakes?
Absolutely, and that's where non-dimensionalization comes in. This is where it gets really powerful. It's about shrinking the complexity of a problem.
Shrinking complexity.
You take your dimensionally homogeneous equation and you divide every term by a cleverly chosen group of variables and constants from the problem itself.
Okay.
And if you choose that group correctly, the dimensions cancel out and the entire equation becomes dimensionless. All the units just disappear.
Wow. Okay. So what's left?
What's left are these pure numbers, these non-dimensional parameters or dimensionless groups. And often these groups turn out to be really fundamental ratios that govern the system. Many have names, named after famous scientists. Reynolds number, Froude number.
Right, I've heard of those. But hang on, for a simple equation, one we could maybe solve anyway, why go through all this trouble? What's the real payoff?
That's a fair question. For simple cases, maybe it seems like extra work. But the advantages become huge when things get complicated or when you want deeper insight.
Okay, like what kind of insight?
Well, first, non-dimensionalization often reveals hidden relationships. Let's take a super simple case. An object falling under gravity in a vacuum.
Okay, basic physics. D2 is dt2 equals Nash GG.
Right. You've got variables like elevation z and time t, and constants like gravity g, initial height 0, initial velocity w0.
Yep.
Now, if you non-dimensionalize this, using 0 and w0 as your scales, the whole equation transforms. And what pops out is just one single dimensionless parameter governing the whole trajectory shape.
Just one, from 3 constants down to 1 parameter.
Exactly. It's the Froude number, basically the ratio of initial kinetic energy to potential energy.
Yeah.
And this single number tells you things you might not easily see otherwise.
Like what?
Like it shows that doubling the initial upward speed has the exact same effect on the dimensionless trajectory shape as decreasing the initial height by a factor of 4.
Yeah.
It reveals these underlying equivalences.
Huh. Okay, that is deeper insight.
And the second big advantage, which you already spotted, is parameter reduction. We went from three-dimensional constants g, w0, 0, 0, that you might need to vary in experiments,
Right.
down to just one dimensionless number, the Froude number. Think about the experimental efficiency.
Yeah, that reduction is massive. So let's make that tangible. Imagine, like, a high school physics class. They're doing experiments, dropping steel balls, maybe varying the starting height and the initial upward push.
Okay.
They do it 10 times, get 10 different curves on their graph paper, 10 separate results.
A classic brute force approach. Lots of data points.
But then they learn about non-dimensionalization. They recalculate their data, plotting dimensionless height versus dimensionless time. What happens?
Magic happens. Well, mathematical magic. All 10 of those different experimental curves collapse beautifully onto a single family of curves.
All of them.
Pretty much, yeah. Or maybe a tight family defined only by that one parameter, the Froude number. Instead of 10 scattered results, you see the underlying universal behavior.
That's incredible. So instead of needing, say, if you wanted to test 5 levels for each of the 3 original variables, that's 5 times 5 times 5. 125 experiments.
Right, a huge number.
With non-dimensionalization, you only need to vary the one-dimensionless parameter. So maybe just 5 experiments give you the same understanding.
Exactly. 5 experiments versus 125 to get the same resolution. It's an enormous saving in time, effort, resources, everything. It turns months in a lab into potentially an afternoon.
Wow.
And connect this to the bigger picture, again, that extrapolation idea. You take that data, those dimensionless curves generated from experiments on Earth, and you can use them to predict, with remarkable accuracy, what would happen somewhere else entirely, like, say, an astronaut throwing a baseball on the moon.
Seriously. From Earth data.
Yep. You calculate the Froude number for the moon throw, find the corresponding point on your dimensionless Earth-based curve, and scale it back using lunar gravity. The prediction for the fall time comes out incredibly close to the exact analytical solution.
So like 3.01 seconds predicted versus 3.05 seconds exact, that kind of accuracy.
That's the kind of power we're talking about. The dimensionless relationship holds true across different environments.
Okay, that's genuinely impressive. So building on that, how does this scale up? How do we use this to predict, say, the performance of a full-size airliner or a car without building dozens of them?
This is really where dimensional analysis becomes indispensable in engineering design. It has 3 main goals, you could say.
Okay.
1, generate those key non-dimensional parameters like Reynolds number or Froude number, which tell you what really governs the physics and how to design focused experiments.
Right, focus the experiments.
2, develop scaling laws. These are the rules that let you take measurements from a small-scale model, say in a wind tunnel, and confidently predict the performance of the full-scale prototype.
Model to reality.
Exactly. And 3, sometimes, even without full experiments, it can help predict general trends, like how changing one variable is likely to affect another.
Got it.
And the foundation for those scaling laws is the principle of similarity. For a model test to accurately predict prototype performance, you need similarity.
Similarity makes sense. What kind?
There are 3 crucial types, and you generally need all 3 for complete similarity. First is geometric similarity.
Okay, that sounds like shape.
It is. The model must be an exact geometric replica of the prototype, just scaled down by a constant factor everywhere. Same angles, same proportions. Think of it as length scale equivalence.
Makes sense. A scale model needs to look like the real thing.
Second is kinematic similarity. This means the fluid flow patterns must also be similar. Velocities at corresponding points in the model flow need to be proportional to the velocities in the prototype flow and pointing in the same relative direction.
So the flow behaves similarly, scaled in time.
Kind of, yeah. Time scale equivalence. Geometric similarity is a prerequisite for this one.
Okay, and the third?
The third, and usually the hardest to achieve, is dynamic similarity. This requires that all the forces acting on the fluid at corresponding points in the model flow scale by a constant factor to the forces in the prototype flow.
All the forces, like pressure, friction, inertia.
Exactly. Force scale equivalence. And kinematic similarity is needed for this. The core idea, the central principle is this. If you can ensure that all the independent dimensionless groups, often called pi groups, we'll get to, those are the same for the model and the prototype.
Okay, match the dimensionless numbers.
Then the dependent dimensionless groups, like maybe a drag coefficient or a lift coefficient you're trying to measure, will also be the same for both the model and the prototype.
Ah, so matching the input numbers guarantees the output number is also matched, dimensionlessly.
That's the key.
Yeah.
Let's take that sports car example. You want to find the aerodynamic drag on the real car.
Right.
You build, say, a 15th scale model and put it in a wind tunnel. Now, for this kind of problem, usually the two most important dimensionless parameters are the drag coefficient, that's what you want to find, and the Reynolds number, which relates inertial forces to viscous forces.
Okay, Reynolds number.
To achieve similarity, you must match the Reynolds number of the model test to the Reynolds number the real car would experience on the road.
Match the Reynolds number. How hard is that?
Well, here's the catch. Reynolds number depends on velocity, size, and fluid properties.
Yeah.
Since the model is smaller, 15th the size, to get the same Reynolds number as the full-size car, doing, say, 50 miles per hour in air, you actually need to run the wind tunnel much faster. For this specific example, the model needs to be tested at a wind speed of about 221 miles per hour.
Wow. 221 mile per hour in the wind tunnel just to simulate 50 mile per hour on the road.
Because of the scaling, yes. It's a challenge, but achievable in good wind tunnels.
Okay, so you run the tunnel at 221 mile per hour. You measure the drag force on the little model car. So you measure 21.2 pounds of force.
Right. Now, because you've matched the Reynolds number, you know the dimensionless drag coefficient is the same for the model and the prototype.
Okay.
Using the scaling laws derived from dimensional analysis, you can then calculate the expected drag force on the full-scale prototype. In this case, it would predict about 25.3 pounds of force for the real car at 50 miles per hour.
So you go from a measurement on a small model to a prediction for the real thing.
Precisely. And notice the actual values of things like air density or viscosity or even the specific speeds, they kind of become secondary. What matters is matching the ratio, the dimensionless group.
That's why you mentioned simulating cars in water tunnels or subs in wind tunnels.
Exactly. As long as you can match the relevant dimensionless parameters like the Reynolds number. In this case, it doesn't matter if the fluid is air or water, or if the object is a car or a submarine model, the dimensionless results will correspond. It's a universal language.
Okay, that's powerful. So we keep talking about these key dimensionless parameters like Reynolds number, Froude number. How do engineers figure out which parameters are important for a new problem? How do they discover them?
Ah, good question. They don't just guess, usually. There's a systematic procedure called the method of repeating variables, which is closely related to something called the Buckingham pi theorem.
Okay, sounds methodical. A recipe.
It's pretty much a step-by-step recipe, yeah.
Yeah.
It lets you figure out the complete set of dimensionless groups, or pi groups, for a given problem, based only on the variables you think are involved and their primary dimensions. You don't even need the full governing equation sometimes.
Really? Just from the list of variables?
Just from the list of relevant physical parameters like pressure, velocity, length, density, viscosity, whatever you think matters, and knowing their dimensions, like mass, length, time.
So what's the process, roughly?
Well, you list all the parameters, identify their primary dimensions, guess how many independent dimensions are involved. Then you choose a set of repeating variables, a core group that includes all the primary dimensions.
Okay.
And then you systematically combine these repeating variables with each of the remaining parameters, one by one, forcing the combination to be dimensionless. Each successful combination gives you one of your pi groups.
Huh. It sounds a bit like algebraic manipulation, but with dimensions.
That's a good way to think about it. You're manipulating the dimensions to find combinations that cancel out. And the amazing thing is how often well-established, famous parameters just naturally emerge from this process.
Like Reynolds number just pops out.
Often, yes. If you include velocity, length, density, and viscosity in your list for a fluid flow problem, the Reynolds number, VELU, will almost certainly appear as one of the pi groups generated by this method. Same for Froude number in flows with gravity, Mach number in high-speed flows, drag coefficients, lift coefficients. They represent fundamental physical ratios, and this method finds them.
That's pretty cool. So it confirms known parameters and can find new ones for unique problems.
Exactly. Let's take a really simple example. Maybe the pressure inside a soap bubble.
Okay. What determines that?
Well, you might guess the pressure difference depends on the bubble's radius and the surface tension of the soap film.
Seems reasonable.
If you run those three parameters through the method of repeating variables, dimensional analysis will tell you that the only possible dimensionless group is Beery-C's.
Okay. So what does that mean?
It means that group must be a constant.
Yeah.
So pair piece must be proportional to spis divided by r. It tells you the pressure difference decreases if the radius increases and increases with surface tension.
So it predicts the relationship, the trend.
Precisely. It can't tell you the value of the constant in this case. For a bubble, the constant is actually 4. But it gives you the functional form, Beery-T equals constant off r, just from dimensional reasoning.
Even without knowing the detailed physics of surface tension.
Right. Or think about a more complex case, like the lift force, FL, on an airplane wing.
Okay. Lots of factors there.
Yeah. You'd include things like airspeed, V, air density, viscosity, speed of sound, C, wing area, A, maybe angle of attack. Dimensional analysis, using the method of repeating variables, will spit out several dimensionless groups. It'll show you that the lift coefficient, CL equals FL, must be some function of the Reynolds number, Re, the Mach number, May VC, and the angle of attack.
So CL function Re Ma.
Exactly. It tells the aeronautical engineer exactly which dimensionless parameters govern lift, guiding their wind tunnel tests or computer simulations. They know they need to control and measure Re, Ma, and I to understand CL.
That's incredibly useful for designing experiments efficiently.
Hugely useful. And let me give you one more example that's just a stunning validation of this whole approach. Friction in pipe flow.
Okay, like water flowing through a pipe.
Right. Dimensional analysis predicts that the friction factor, F, which tells you about pressure loss, should depend only on the Reynolds number, Re, of the flow and the relative roughness of the pipe wall. Re d, roughness, height over diameter. So F function Re in dB.
Just those two dimensionless groups determine the friction?
According to dimensional analysis, yes. Now, here's the amazing part. People run sophisticated computer simulations, computational fluid dynamics, CFD. They can simulate, say, water flowing in a specific pipe, and they can simulate air flowing in a completely different pipe, maybe much larger or smaller. Different fluids, different scales, different absolute pressures and velocities.
Okay.
But if they set up the simulations so that the Reynolds number and the relative roughness, everyone, are identical in both cases.
Even though everything else is different?
Even though the actual physical shear stress on the pipe wall might differ by orders of magnitude between the water pipe and the air pipe, the dimensionless friction factor, calculated by both simulations, comes out almost exactly the same.
Wow. That really proves the point, doesn't it?
It's a beautiful confirmation. The dimensionless parameters truly capture the essential physics, independent of the specific scale or fluid.
Okay, this is clearly incredibly powerful. It simplifies problems, guides experiments, saves massive amounts of effort. You said maybe 5 tests instead of 125.
Or even more, for complex problems with many variables.
But what happens when you can't achieve that perfect similarity? You mentioned matching Reynolds number for the model car meant running the wind tunnel really fast. What if you just can't do it? What if matching one parameter prevents you from matching another?
That's a very real and common challenge in experimental work. We call it incomplete similarity. It's often impossible to match all the relevant dimensionless parameters simultaneously between a model and a prototype.
So what do engineers do then? Give up?
No, they don't give up. They get clever. Let's revisit that wind tunnel test, maybe for a model truck this time.
Yeah.
Say a 1/16 scale model.
Right.
A full-size truck going 60 mph per hour has a certain Reynolds number. To match that Reynolds number with the tiny 1/16 scale model, you need to run the wind tunnel at something like 429 meters per second.
Whoa, that's faster than sound, isn't it?
Yeah.
Mach 1 is around 343 meters.
Exactly. It's supersonic. But the real truck isn't going supersonic. So now you have a problem. Matching the Reynolds number would mean wildly mismatching the Mach number, which also affects aerodynamics at high speeds. You can't match both Re and Ma.
So incomplete similarity, what's the workaround?
Often engineers rely on a phenomenon called Reynolds number independence. For certain types of shapes, particularly bluff bodies like trucks or buildings that cause a lot of flow separation.
Things that aren't streamlined.
Right. For these shapes, the drag coefficient often becomes pretty much constant once the Reynolds number gets high enough. It kind of levels off on a graph.
Ah, okay.
So engineers might test the model truck at the highest achievable Reynolds number in their wind tunnel, even if it's lower than the prototypes. They check if the drag coefficient seems to have leveled off at that point.
And if it has?
If it has, they make the reasonable assumption that the drag coefficient would stay at that same level even at the much higher Reynolds number of the full-scale truck. They use the measured model drag coefficient to estimate the full-scale drag.
So they use the model data, but with an understanding of where similarity breaks down and how to compensate.
Exactly. It's an engineering judgment based on understanding the physics and the data.
What about other cases? Are there other situations where similarity is tricky?
Oh, definitely. Flows with a free surface, like testing model ships in a towing tank or building models of rivers or dams. They have extra complications.
Free surface, meaning the water surface exposed to air.
Right. At very small scales, surface tension forces, which are usually negligible for a real ship or river, can become disproportionately large in the model and mess things up.
So you get unwanted effects.
You can. Also, the flow regime might change. A big river might be highly turbulent, but a small-scale model of it might end up being smooth, laminar flow, which behaves differently.
And I guess matching parameters is hard there too.
Extremely hard. For ship models, for instance, both Reynolds number, related to friction drag, and Froude number, related to wave-making drag, are important.
Okay, need to match both Re and Fret.
But if you try to scale things to match both simultaneously for, say, 1100 scale model ship, you find you'd need a test liquid with an incredibly low kinematic viscosity, like something much less viscous than water, which doesn't really exist practically. It's often impossible.
Another impossible situation.
Yeah.
So what's the compromise there?
Usually for ships and river models, matching the Froude number is prioritized because wave effects are often dominant.
Focus on Froude.
Yeah. And then they try to deal with the Reynolds number mismatch separately, perhaps by using empirical corrections for friction drag, or by trying to artificially roughen the model to encourage turbulence, or again, relying on Reynolds number independence if possible. It's about making the best possible prediction given the unavoidable limitations.
So it's not always perfect, but dimensional analysis still provides the framework for understanding what needs to be matched and how to interpret the results, even when you can't match everything.
Precisely. It tells you what you're missing and helps you account for it.
So, okay, thinking about this, how does this maybe show up for us, in everyday life? Does this similarity stuff appear anywhere unexpected?
Well, here's a fun one. Next time you're watching a movie with special effects, especially older ones, pay attention to miniature models used for things like fires or explosions.
Okay.
Sometimes they just look wrong, don't they? A fire on a model building might look too billowy or slow, or an explosion might not seem powerful enough.
Yeah, I know what you mean. It doesn't look quite real.
That's often because of a lack of dynamic similarity. To make a small fire look like a big fire, you need to scale the fluid dynamics correctly. This involves things like the Froude number, gravity's effect on the plumes, and maybe Reynolds number. If they just light a small fire on a small model, the dimensionless numbers are all wrong, and your eye instinctively picks up that the physics isn't scaling properly. It doesn't look like a real full-scale fire.
Huh. So bad special effects can be a failure of dimensional analysis.
In a way, yes. They haven't properly scaled the dimensionless parameters governing the phenomena.
That's brilliant. Any other cool examples?
There's a great one from biology, studying how insects fly. Trying to measure the forces on a tiny, rapidly flapping fruit fly wing is incredibly difficult.
Oh, I bet.
So researchers built a robotic fly wing model. They called it RoboFly. But here's the clever part. The model was 100 times larger than a real fly wing.
Bigger, not smaller.
Bigger. And they flapped it 1,000 times slower than a real fly. And they did it not in air, but submerged in mineral oil.
Mineral oil. Why?
Because mineral oil is much more viscous than air. By carefully choosing the larger size, the slower speed, and the properties of the mineral oil, they were able to perfectly match the Reynolds number of the real fruit fly wing operating in air.
Ah. They manipulated all the scales to achieve dynamic similarity, even though it looked totally different.
Exactly. Because they matched the key dimensionless parameter, Reynolds number, the aerodynamic forces measured on the giant, slow-moving RoboFly wing in oil could be accurately scaled to understand the forces on the tiny, fast fly wing in air. It allowed them to study insect flight in detail that was otherwise impossible.
That is a fantastic example of using these principles creatively.
It really shows the power of thinking dimensionlessly.
Okay, so let's wrap this up. Today, we've really peeled back the layers on dimensional analysis and modeling. We went from the basics, dimensions, units, that crucial rule of homogeneity.
Can't add apples and oranges.
Right, all the way to the method of repeating variables, Buckingham pi theorem, for actually finding those key dimensionless parameters.
And seeing how they let us achieve similarity between models and prototypes.
Yeah, and you've seen how this tool, which might seem a bit abstract at first, lets engineers simplify incredibly complex problems, design much smarter experiments,
Saving huge amounts of time and money.
and predict how things will behave in the real world across totally different scales. Even when perfect information isn't available or perfect test conditions are impossible, like with incomplete similarity.
It provides the framework to make sense of it all.
So maybe a final thought for you to consider. Just think about the elegance of it. How these fundamental physical laws, just expressed through their basic dimensions, mass, length, time, how they allow us to unlock secrets and predict behavior for everything from, like you said, a tiny fruit fly's wing, all the way up to a massive ocean liner or an airplane. Sometimes, even when we don't have all the pieces of the underlying physics equations figured out, it's like a universal code for how the physical world scales.
It really is a remarkably powerful perspective.